that will be given by Tongyang Lee, and he will talk about quantum algorithms on convex bodies.
Thank you. I want to first thank for the organizers for inviting me to give the talk here. Today I'm going to mainly talk about quantum algorithms on convex bodies. So what is the motivation for this topic? I think the previous two talks by Richard and Anupam, they have been talking about fast quantum algorithms for assuming SDP, quantum programming, etc. I think with explicit matrices stored in quantum data structure. So this is really some power that basically we have the data structure and there's something microscopic. But I think another question to ask is to see this problem more macroscopically. That for instance, what if you don't have the explicit matrix input, but maybe only some implicit oracle access? What can we do with convex formalization, and what is the corresponding quantum speedup? So what do I mean by implicit oracle access? So in particular, for instance, like important convex formalization problems, like the LP, like the SDP, and many others, when we talk about convex formalization problem, they have convex feasible region, a convex body K that is in an n-dimensional real space. So a common oracle access to talk about a certain convex body is the membership oracle, where you assume the ability to test whether a point in the region is inside the convex body or not. So it's basically a function, the membership function, that returns 1 if your point inside the convex body, or it equals to 0 if point is outside the convex body. The main topic today is going to talk about what can we do only on a convex body with just like this very general information about the convex body, but with the membership oracle, only with this kind of quantum superposition access. That is basically to say a quantum unitary oracle that maps the quantum state x0 to the quantum state x mem kx, where the mem kx is a Boolean value that equals to 1 if your x is inside the convex body or equals to 0 if not. So this is really like a very general problem and a very general definition about a certain problem set. So speaking about a convex body, what is probably the first question that maybe you want to ask? Maybe the very first question is that given a convex body, you want to, for instance, estimate its volume, which is going to be defined as the integral of the identity function on this convex set. So to be more specific, for the volume estimation problem, we also have a certain input epsilon, which is the error, and we are both basically going to return a value that is between 1 minus epsilon times the volume and 1 plus epsilon times the volume with high success probability. Why do we want to study this problem? I think this is basically at the very beginning one of the most natural problems that if you want to play with a very general convex formalization. And also, speaking of the merits of the problem per se, it is really one of the most basic problems in geometry. And also, when talking about this connection, yes?
Can you comment about the measure? Is it just a flat measure induced by these? Can you comment on the measure?
The measure of what?
Ex.
Yes, it's just like an integral on this real space. So it's just like a convex body. What is the confusion? Okay.
It's the number of points in K, right?
Yes, yes. So the K here is a convex body. It's really like a continuous convex set.
Number of things in K.
Well, it's like the number of things is uncountable because it's just, it should be an integral here.
Oh, sorry, of course.
Yeah, this is really, we're talking about the K here is a continuous set. Yeah, and you have to like define it as an integral of the corresponding region. Yes?
So you said the membership oracle, you submit a vector x in Rn and it tells you whether it's inside the body or outside. But this is like a vector of real numbers. What should I think of like as just all the entries being like there's some constant precision? Or?
Oh, yes, yes. So you can just imagine the x here to be represented as floating numbers. And for floating numbers, I think they just maybe have 64-bit, something like that. And there can be some error inside here. But I think also on the other hand, I think our oracle is robust to the error that if you have some slightly error dependence, does not influence the problem by much.
Okay, so now I'm asking, is volume K infinite?
Sorry? No, it's finite. Yeah, I think later on I will be more careful about how we are going to characterize the problem. Any other questions? Okay, so I think on the one hand, this problem is very natural because it is one of the most basic problems in geometry. And also on the other hand, speaking of the connection to quantum computing, I think this can be viewed as a continuous version of counting. And I think quantum counting in general has been widely applied to Galois type algorithms. And if you have a good understanding about the volume estimation problem, we may also consider some continuous counterpart of many other quantum algorithms. So I think we want to be a little bit more clear about like how we are going to formulate the problem. So in particular, as I just mentioned, the input model is going to be this kind of quantum oracle. And I think there are some other regularization constraints for the problem. So for instance, we assume the original point inside the convex body. So this is just to make sure that, for instance, if the convex body is not on the Earth, then we probably cannot give a good quantum algorithm for that. So we just assume the original point inside the convex body. And also we assume some sort of information, like a condition number of the corresponding convex body, where we assume the convex body is contained in a really large ball with radius capital R and contains a corresponding small ball with radius small r here, where this, the B2 just represents the corresponding ball in the sense of L2 norm. So classically, the best known classical query complexity for solving the volume estimation problem, given this kind of assumption where the original point inside the convex body, and also some sort of condition number, the capital R and small r here, the classical best known query complexity is only n to the 4 by Loache and Van Pelle in 2003. And actually, this is, although this is like one of the most important problem, this problem is known to be notoriously hard. And you see like this classical query complexity of n to the 4 has been standing for more than 15 years. So very recently, we gave a quantum algorithm that can solve the volume estimation problem using only n to the 3 plus n to the 2.5 over epsilon quantum queries for the quantum queries to the corresponding membership oracles, where the tilde O here omits polylogarithmic factors. So in particular, it only like the dependence on the condition number, like capital R over small r, is only polylog, and also it also contains some other terms like log n and log 1 over epsilon. So how do we compare this to classical state-of-the-arts? Like the classical best-known algorithm, as I just mentioned, like due to Loache and Pelle, has n to the 4 complexity. And I think it can be slightly polished down in a later work due to constants of Van Pelle, and the total complexity can be like n to the 4 plus n to the 3 over epsilon squared. Whereas our quantum complexity, you see like it's both better in n, and also like the epsilon dependence is quadratically better. And speaking of the total arithmetic complexity, like both the quantum and classical algorithm is blown up by a factor of n squared. So it's like classical it is this, but quantum is this. So after all, I think we have both quantum speed up for the query complexity and arithmetic complexity of the volume estimation problem.
So the best known query causes n to the 4, but is there a lower bound for this in the classical setting?
Yes. The classical best known lower bound is due to Rademacher and Van Pelle, which is n to the 2 over log n, roughly n squared.
N squared.
Yes. Ultimately, we have a squared of n quantum lower bound, which is probably far from tight, but hopefully we can later improve it. But I think at least our quantum lower bound gives a conceptual message that for this very general case, like you have like a very general convectomization problem and a membership oracle, especially about the volume estimation problem, the quantum speed up can be at most polynomial. Okay, so let's delve more into the problem now. So speaking about the volume estimation problem, what is the first thing that you can probably think about maybe on top of your head? Maybe like a very naive algorithm is just like a Monte Carlo approach, which just you do the counting brute forcefully, something like this. But actually it doesn't work very well because the volume actually takes an exponentially large range. Because for instance, if it's only known to be contained in a large ball of radius capital R to the n, of radius capital R, then the volume can be, roughly speaking, as large as capital R to the n, as small r to the n. This is really like exponentially large range, and probably just like a brute force counting argument will take exponential calls and doesn't work well in practice. So instead, what is the strategy that we are going to use here? So maybe we want to consider some parameterized value like this. So what is the motivation for considering this kind of like partition function? I think on the one hand, it has the nature that the z0 value being equals to the volume of the convex body. But also on the other hand, if you take to another extreme, because the exponential function actually decays exponentially fast with respect to the L2 norm of the value of the x here. If you choose a large enough a here, it will ensure that the value za is going to be close enough to a fixed value, which you don't have to really take the whole integral on the convex body. But it suffices that you only take the integral on the small ball, because like otherwise like the outside part it really decays too fast, and this is actually a good estimation of the value za here. So I think this is really going to motivate us, and in particular, I think this actually corresponds to the simulated annealing strategy, where maybe we want to consider sequences, a sequence of values from A0 to A1 to AM, where the A0 here is sufficiently large, but finally the AM here is going to be small enough, and it is actually going to be very close to 0. And we iteratively change the values from AI to AI plus 1, and we estimate the volume of the convex body by a telescoping product like this. Okay, so this is really going to give the motivation because on the one hand, on the left-hand side, this is something we want, and at the very beginning, this is something we know. But on the other hand, how we want to estimate each telescoping ratio. We are going to, for each telescoping ratio, take some ID samples inside the convex body, and we are going to take the average. So what do I mean by that? So in particular, if you are given the ability to sample from the corresponding density like this, e to the minus ai times the L2 norm of the value of x, and if you denote this random variable, denote output as a random variable xi, and we correspondingly denote a random variable vi like this, then the expectation of this random variable, if you take the corresponding integral and just make a calculation, it is just going to be the telescoping product that you want. So the essential problem here becomes like we don't really, we actually make a reduction from the estimation of each telescoping ratio to give a good random walk that is really going to sample from the corresponding density like this. And how we are going to do this? I think in the Loaz and Pella paper, they actually use a specific kind of random walk inside the convex body called the hit and run walk. And actually, it constitutes 2 steps. So where for the first step, you are going to, for instance, assume you are currently at a point P1 here. You are going to pick a uniformly random line L through the current point P here. So for instance, if you just draw a very small sphere here, you just like pick a random point on the sphere here, maybe this point, you just like shoot this corresponding chord here. And for the second point, so after you shoot the chord, which is going to intersect with the corresponding convex body, you are going to move to a random point along this chord, and with the which is going to be proportional to this density. So what is the main argument and what is the main observation here? So in general, walking in n-dimensional space is a very difficult task, and in general, it suffers from the curse of dimensionality. But this gives a very natural reduction from an n-dimensional walk to a one-dimensional walk, and actually works very well. And in particular, in the Loaz and Pella paper, it actually follows this simulated annealing strategy, where the simulated annealing algorithm in total is going to have square root of n iterations, and inside each iteration, they are going to take square root of n or epsilon squared IID samples, such that you are going to give a good precision of the estimation of the telescoping ratio. And for each sample, basically, each sample come out of the hit and run walk. Actually, it is going to take about cubic step of the hit and run walk, given the promise that your convex body is well-rounded. By well-rounded, I mean the condition number is at most square root of n. So why do we really stick with the value of square root of n? Because this really naturally appears in a lot of convex bodies in the n-dimensional space. So in particular, if you think about like a unit hypercube, it just has the condition number to be square root of n. And if you consider like a sphere, the corresponding condition number is very good, it's just 1. So at least the Loaz and Pella, for now, they give a good classical algorithm for the volume estimation problem under the well-rounded case. But also, on the other hand, you can consider some reduction, like for being well-rounded, maybe, for instance, one axis is just too long, the other axis is too short. But maybe you can consider try to construct some affine transformation that really, for instance, if you have an exploit here, you want to punch it to a sphere here, which is going to be looking very good and which is actually going to be well-rounded. And in fact, the Loaz and Pella, they give a classical algorithm that only using n to the 4 classical queries to making such kind of affine transformation to make the input convex body well-rounded. So in total, the complexity, like summing through this kind of well-rounded maybe we can regard this as a pre-processing step, and also like the corresponding simulated annealing algorithm, the total complexity is going to be n to the 4 over epsilon squared. So let's make a quick summary here about the success of the classical volume estimation algorithm. And actually, there are 3 key factors. So for the first factor, it actually, high-levelly speaking, this is actually a simulated annealing algorithm where the volume is going to be estimated by a product of some telescoping ratios. And for the middle level, we are going to take some IID samples such that we can give a good estimation of each this kind of telescoping ratio. And in other words, I think it is very important that the random variable that comes out of the corresponding walk is very small. And for the low level, we have to think about some implementation of the corresponding walk. And in particular, it requires that the corresponding random walk converges fast such that we can really efficiently take IID samples. So this is basically like the rough story about a volume estimation algorithm. So how we are going to think about like a corresponding quantum volume estimation algorithm. maybe we want to question us from also from the 3 levels: high level, middle level, and low level. So for instance, at the high level, maybe a very natural question to ask is that whether we can consider like a quantum similar annealing framework. And for the middle level here, because really we are going to give estimation about the each telescoping ratio, and this is really something like amplitude estimation, and maybe we want to ask us that whether we can give a quantum speed up by quantum counting. And for the low level here, because like the classical algorithm, for instance, the hit and run walk, is really something very closely related to previous theories of quantum walks. Maybe we also want to ask whether such kind of speed up is possible. Okay, so I think maybe for my talk, I'm going to go through these different levels separately. Maybe let's first go with the low level. So as I just mentioned, like for instance, there has some been previous theories about quantum walks, especially for instance, Segedie theory. But I think the main consideration has been happening in the discrete space. So how we are going to consider some continuous space quantum walks. So this is somehow like we are going to just like move from the discrete space to the continuous space using Segedie theory. And furthermore, we can actually show the Chigurh inequality for the continuous space Markov chains. And actually, in our paper, we give a very detailed analysis about how we are going to relate such kind of like continuous hit and run walk to a discretized version. And basically, we give a very good analysis about like how the conductance is going to change when we move from the continuous case to the corresponding discrete case. And actually, what is the result here? So if like for instance, the classical Loas and Hella paper, if they can show that their hit and run walk converges in cubic time, then also on the other hand, we can show that our quantum hit and run walk operators, unitary operators, have spectral gap at least n to the minus 1.5. Excuse me. So this is a very rough understanding about the low level. Maybe we also, like on the other hand, we want to get an understanding about the high level, about the simulated annealing framework. We are going to, in particular, utilize a simulated annealing framework due to Watson and Abayasinhi, which is going to talk about some, because it very naturally talks about quantum walk operators, and which is the case that we use for our quantum version of the hit-run walk. We have corresponding quantum walk operators, maybe from W1 to WR in a simulated annealing procedure, and correspondingly, they have stationary states from W1 to pi1 to pi r. And because this is a simulated annealing schedule, like the overlap between consecutive stationary states, they should be large. Like for instance, the inner product here should be at least p here. We also denote like the delta to be the general lower bound on the spectral gaps of the quantum walk operators. So a very natural question here is that how we are going to change from the very start stationary state pi1 to the final stationary state pi r that we really need for the simulated annealing schedule. So by doing this, we are going to consider really some amplitude amplification kind of things, but we use like an alternate version, which is called fixed point search, and also called pi/3 amplitude amplification, where instead of the normal Grover that having like a pi angle here, we only have a pi/3 angle here, and we consider such kind of pi/3 reflections. Its main merit is that it won't have the problem in the original Grover algorithm about overshooting. And actually, in general, if you apply this kind of pi/3 amplitude amplification iteratively, you are going to get very close to the next state that you are going to need. So this is actually the very important building block of our quantum algorithm. And through like the quantum simulating strategy, we are going to apply pi/3 amplitude amplification throughout, from the very beginning state pi1 to pi2, and finally to the state pi r that we need for the volume estimation algorithm. And also on the other hand, we take the simulated annealing schedule slow enough such that the overlap, the p here is a constant, and I actually make sure that m here, like the number of iterations for the pi/3 amplitude amplification, is only a constant in each iteration. And the total complexity for this framework is going to be r over p times delta, where the delta, recall the delta is here the spectral gap of all the quantum walk operators, and p here is the overlap between consecutive stationary states. So in our quantum algorithm for volume estimation, the r here, like the total iterations for the simulated annealing schedule, is going to be square root of n. And as I just mentioned, each wi here is going to be the quantum hit and run walk operator with density proportional to the corresponding exponential distribution. And also on the other hand, we know that pi0 is easy to prepare. It's just like we just have to really prepare the density on the small bulb here, because the density really decays too fast, and we don't have to worry about the things outside. And also the spectral gap, as I just mentioned, for the low level part, it at least n to the minus 1.5. So in total, this really gives a good simulating schedule that we can actually implement our quantum algorithm. But the only remaining question here is that how many states here do we actually have to prepare such that overall we can give a good estimate for each telescoping ratio by quantum counting with high precision and actually reach the high success probability that we need. So this is really the quantum counting part. Maybe let me just very briefly recall this. So we assume that we have a unitary U here that maps the state 0, 0 to a state which has the amplitude square root of p here. And I think in general, compared to the classical, for instance, like a Chernoff bound, then basically quantum we can actually reach only O of 1 or epsilon cost to give a good estimate about the probability p here compared to a classical sampling procedure. So in general, here there is some further technique developed by Hamodi and Magnius, which is called quantum Chebyshev inequality. In general, if you have a unitary that corresponds to a certain random variable, which is going to be a summation like this, then basically this technique due to Hamodi and Magnius that can also make everything go through. We are actually compared to a classical version of the Chebyshev inequality. The dependence on the variance and also the dependence on the epsilon here can both be given like a quantum quadratic speed up. Sorry. So using this quantum Chebyshev inequality and also give on the very important observation in the volume estimation algorithm, actually the variance here is very small because the simulant annealing is slow enough, and such kind of procedure is called Chebyshev cooling. Actually, we can, if we put the corresponding quantum Chebyshev inequality into our framework, we can notice that if there are a square root of n or epsilon square classical samples for estimating the classical telescoping ratio, then quantumly we only have to use square root of n over epsilon quantum copies of the states pi, such that we can give a good estimation of the telescoping ratio. So let's make a summary about the quantum algorithm here. So for the high level here, we can adapt the quantum simulated annealing framework, and actually the total number of iterations is square root of n. For the middle level, we are going to replace like a classical sampling procedure by a quantum Chebyshev inequality, and the total number of calls to the quantum hit and run walk operator is going to be square root of n over epsilon. And for the low level, the number of queries to implement each step of the quantum walk operator is going to be n to the 1.5. And also, I don't have the time to cover here, but also we gave a rounding algorithm that really like punch a very EO condition convex body to a well condition case, only using cubic number of quantum queries. And in total, like the quantum query complexity of our algorithm is the n to the 3 plus n to the 2.5 or epsilon, as I claimed at the very beginning of my talk. And speaking about arithmetic complexity, so why the classical and quantum complexities are both blown up by a factor of n squared? This is basically because of the rounding part. The rounding part is actually the Fn transformation is an n-dimensional matrix vector product. So very naturally, like quantum and classical algorithm, speaking of the total arithmetic operations, like in our quantum cases, n to the 5 plus n to the 4.5 or epsilon. So this is basically the quantum algorithm for volume estimation. Is there any question?
Question.
Yes.
Real numbers, but you're in a quantum computer, so you've discretized it in some fashion?
Yes, yes. Yes. So I think in my talk I didn't cover it very carefully, but in the low-level part I talk about this quantum hit and run walk operators. So we have a theory about like basically we deal with everything in the continuous space, but in a specific section of our paper we also talk about its corresponding discretized version. So for instance, you only have grid points. It's just like imagine you have like a really, really fine grain, like grid for your corresponding convex body. You can also correspondingly define your hit and run walk on that. And I think a very important thing is that if you consider corresponding grid fine enough, then the corresponding conductance, the lower bound on the conductance of the discretized hit and run walk is going to be very close to the conductance of the original like continuous hit and run walk. And actually, in practice, we are just going to use the discretized version of the hit and run walk.
It's the same for the oracle too, right? You're not inputting a real number. You're just
Yes, you can say that. Yes.
So how many points do you have if in each dimension?
Each dimension.
The scale with n?
I think so. I kind of forgot the details.
Okay, forget it. Okay.
Yeah, but it is not. I think it should definitely be a polynomial of n. Probably something just like linear. Yes. Sorry?
Where did you use the convexity?
Oh yes. So if your body is not convex, then like the conductance is, you just totally have no clue for the conductance. For instance, maybe your is there any marker? Oh. Yes. So the convexity here mainly appears in the walk part. So for instance, if you have like a really bad convex body, maybe something like this, then maybe if you just consider the heat and run walk like doing this, doing this, I think maybe at some point you are feeling good because, for instance, maybe you get enough information about this point. But actually, for instance, maybe this is a sausage, and for the most part of the sausage, you just have no information. Your walk just cannot reach it. In general, it's just like for a non-convex body, it's just impossible to give like a corresponding walk with a reasonable conductance, which is going to be like the main issue of the corresponding algorithm, both classically and quantumly. Any other questions? Yes.
No hope for speed up on these arithmetic operations?
Oh, that's a very good question. I don't know, actually. I think in general I guess I'm not sure if my talk is a little bit too difficult and probably baffles some of you. But I think in general, this problem is just like very important but notoriously hard, even classically. And I don't think like classically people have a good information about how we are going to improve like the total cost here. Yeah, I don't know. Other questions? Yes.
This is more like a comment, but like somebody asked about what's the measure there. Like in principle, you can imagine you could, instead of integrating just the unit function, you can integrate some other function. And I guess if the function is convex, then you could kind of add one more dimension, and you have like another convex body, and you could also basically evaluate convex integrals also using the same idea.
Yes. I think that is a very good point about like basically about improvement on the integral. I think in general our algorithm can be directly adapted to give integrals for log concave functions. I think in general for log concave functions, just like if you take a log, it's a concave function. I think the main merit is that basically exponential function is one of the most important log concave function. Basically make a corresponding adaptation, then everything works through. But I guess your observation is probably also a very nice observation about making integrals. Yes.
Somehow intuitively I expect the standard simplex to be like a very, very bad example for the classical algorithm. Because kind of like the conditioning you mentioned is like as bad as it can be, right? Because it's like in case for Löbner ellipsoids. But at the same time I expect that like maybe this is a particularly easy set for a quantum algorithm. If you looked at like specific instances like simplices and how the two methods compare there.
Oh, that's actually a very good question. I think in general a very important like a line of classical works for volume estimation. This is really very general about convex body. But for instance, what if I tell you more information? Say, what if like the convex body is known to be a polytope, and whether can you give a faster classical algorithm for volume estimation? The answer is yes. So actually a very important open question along this line is specifically about the example of the polytope. So for polytope, you see it's just like a linear programming here. And I think the main question here is that whether we can adapt some of the technique here to maybe some of the HHL type of algorithms, like in general, for instance, like Andrews framework for singular value transformation. Because actually, you see classically, there's actually a gap about like between like linear algebra, so the linear system, to the corresponding optimization problem. And in particular, like volume estimation of polytopes is also a very important such kind of problems. And maybe we can try to utilize more structure. But this is definitely a very good question. And also, I think some of the future works I do want to explore in the future. Any other questions? Okay, so I think this is one part of the talk, and I think probably because of time limitation, maybe let me also sketch about the next part of the problem. Yeah, sorry. Yeah, I think. Oh, yeah, sure. I think also for this part, because like this is probably it is an older result that actually appeared in 2018. So I think the point is that after having a quantum algorithm on convex bodies, maybe you also want to, in general, because this is really a session for convex optimization, what if like I just give you a convex function and you correspondingly solve the convex optimization problem? And here the oracle, like compared to the classical counterpart, is going to be evaluation oracle, which is a unitary map to the state x0 to the state xfx. And like the goal here is, as I just mentioned, is this. And actually this is a very like well-studied classical problem. And the state of the art in the classical side is due to Lee from Hella having like quadratic number of classical queries and runs in cubic time. So the main result actually achieved by us and also independent work by Evan Appleton, Gillian, Gribling, and DeWolf, that basically for the convectomization problem, we can give a quantum algorithm for both the membership oracle and evaluation oracle only using linear number of quantum queries, and we can show correspondingly a square root of n quantum lower bound. And furthermore, like the additional arithmetic complexity of our quantum algorithm is similar to the classical counterpart. So what is the outcome for this? So this is actually the first non-trivial quantum upper bound on this very general convectomization problem. And also, it also, similar to the volume estimation problem, shows the impossibility of the generic quantum speedup for convectomization. And actually, the speedup is the most polynomial. So maybe let me just quickly go through the rest of my talk. But I think the strategy here is that in general, you can reduce the convectomization problem to like a convectomization problem with a very general convex function, but consider corresponding like ifn side, and basically can be reduced to n plus 1 dimensional convectomization problem, but the corresponding function is linear. So having this kind of idea, and I think the next thing we are going to, it is going to be considered is two different oracles, where for the optimization oracle, you just solve the problem, but for the separation oracle, you are going to construct a separation if you have a point not inside the convex body, you are supposed to construct a separation hyperplane between this point not inside the convex body and the convex body per se. So classical, the Lisa from Hella work make a very important contribution that the reduction from the separation oracle to the membership oracle only takes linear cost, whereas quantumly we can show that this reduction only takes polylogarithmic cost. And actually this is going to be achieved by, I think the idea is going to consider a corresponding function, because in general, maybe let me just draw, that should be quicker than saying. So
maybe that's the last drawing. And then
yeah, definitely. Yeah. So if you have a point outside the convex body and you want to consider the separation oracle, a very natural way, because you know the original point inside the convex body, you just line this segment, and basically you consider, because you have the membership oracle, you roughly know the boundary of the convex body, and you just call this distance function to be the height function here. And I think it suffices that you can take the subgradient, because like in general the convex body might not be smooth, so it probably does not have a gradient, but has a subgradient that basically considers a subgradient is going to be tangent to the convex body, and actually it is going to be given a good separation oracle. And this is actually going to be given by Jordan's algorithm, actually, which is a clever way to use the quantum Fourier transform. Okay, so maybe I think let's just very quickly summarize. So the conclusion here is that we gave two quantum algorithms on convex bodies. So the first algorithm is for a volume estimation of convex bodies, which actually we have a corresponding quantum speedup, and also sure. Yes. And also, we very briefly talk about the quantum algorithms on convex bodies, like on convectomization, solving these very general problems. So let me list a few open questions. So first, can we apply our simultaneous framework to solve other problems such as partition function estimation? And maybe also can we, like in general, maybe go like beyond out of the session. I think this session mainly talk about convectomization, but maybe also of interest to talk about non-convectomization problems. And at last, I think, can we actually prove better quantum lower bounds? I think for both problems, like the current quantum lower bound is really bad, and I think we want to really improve ourselves. Thanks for your attention.
I guess one quick question. And a quick answer also.
Sure.
So on the subject of using simulated annealing to do partition function estimation, hasn't that already been addressed by like work by Montanaro and more recently by Harrow and Wei?
Yes, exactly.
Is there more, do you think, that can be done in that direction, or?
Yes. I think speaking of partition function, this is really larger topic, like partition function of what? I think they basically, the Montanaro's work and the Harrow and Wei's work, they basically talk about function that's defined on a discrete space. But in general, there may be some, and also I think like the discrete of a certain cardinality known to be n. But in general, if you consider a lot of physical systems, there may be some other kind of partition function that maybe you also want to estimate. I think like to be more like general, for instance, like a lot of SDP algorithms, I think the Gibbs state can also be regarded as a certain kind of partition function, because you have this kind of trace under the trace in the denominator of the definition of the Gibbs state. So there are definitely a lot of different things to explore. But yes, I think for the speaking of the Harrow and Wei's work, actually we have some of similarities in the technical details of the work. But I think it is also a very nice one. But I think there are definitely more things to explore along this line of research.
Thank you very much.